Sarthak, you can call Sanket.
Yes, sir. Yes, sir, is coming.
Shall we start? Sarthak, you can share the screen and go ahead.
Okay, sir. Am I audible? Hello, am I audible?
Yes, sir.
Yes, Gaurav.
Um, so please read the first question. Uh, so in this is a second order system, and it has a single zero, and we know that tau 1 is greater than tau 2, and you have to prove these four things. So what you can, and this is for a step input. So we know that x of s is something like a constant by s. So you can start by uh, performing a Laplace transformation on this, and then uh, try to do these four questions.
Yes, so thank you, Sarthak. So the question is all about, so you are given with, of course, as a converter transfer function with some condition, and you have been asked to show various conditions when it has an extremum. Extremum could be maxima or minima, when it can be inverse response, when you will have overshoot, etc. Hello, are you there, all of you? So what you have to look for is how do you calculate the extremum. So how do you compute the max or minima? Take the first derivative, go to 0, then identify something, then apply what, look for the condition of inverse response, etc., etc., and look for the condition of overshoot. So check whether you are able to do it with this condition. Maybe we'll wait till 1:15, then you can explain.
Okay, so because it was a step input, so we know that x of s was we have taken it as m by s, and so you can find out this y of t as this equation by Laplace transformations. And the first part was y of t can exhibit a extremum if the in the response only if this quantity is greater than 1. So for that, we know that we have to take the first derivative of this equation. So when we take the first derivative and equate it to 0, we will get this condition. And we know that exponential minus t of 1 minus tau 1 minus 1 upon tau 2 will be greater than equal to 1 because tau 1 is greater than tau 2. So this quantity is greater than 1. For the second part, if an extremum in y exists, the time at which it occurs can only be found analytically in what it is. So we have to, from here, we have to equate it to 0. Uh, uh, the first derivative equated to 0 and then get the value of t. So we can get the value of t by simply taking natural log on both the sides. Uh, and we'll get this t equals this equation. For the third part, inverse response occurs only when TA is uh, less than 0. So for that, we know that uh, it then we know that the 0 should be positive, and in this case we have only 1 0, and that is minus 1 upon tau a. And for this to be positive, tau a should be negative. So this is the condition. And the next is we have to show that the overshoot occurs only when tau a upon tau 1 is greater than 1. So for that, we have to see yt is greater than km. And by doing this, we get as above, we can get this condition. And we can show that tau a is greater than tau 1 when the overshoots happen. Uh, so any questions? If not, please try the second question.
So any questions in understanding this? So here you have been asked to you have been asked to figure out that understanding regarding how those conditions exist, right? So please apply those specific condition. I think that's all about the problem. So if you have any questions, yes, please let us know. Otherwise, let's go to the question number, next question. Okay.
So you can start with writing the transfer function of this thing, and then try to answer these questions.
So can gain be an infinite value?
So gain technically cannot be infinite. Then what does that mean? How do you define a gain? Rate of change of output by rate of change of input, right? So then what you are saying that there is an output, even there is a rate of, without there is a change in input. You see that? So technically, no. Yes, that's the answer.
So the first part is what is the overall transfer function? So the overall transfer function is you need to basically add both k1 by s and k2 by tau s plus 1, and this will be the final uh, transfer function. And then you need to put it in the standard form to get the value of k and tau. Uh, the next part is what is the gain. So yeah, so the gain of this transfer function will be k1. When we compare it to the standard form, we get k1, and gain can be negative if uh, k1 is negative. The next is the poles and where are they located. So the poles will be, you can see the denominator part as s into tau s plus 1. So there are two poles. One is s1 is 0 and the other one will be minus 1 by tau. So S1 will be on imaginary axis and the S2 will be in the left hand plane. The next part is what are the zeros. So the zero will be the numerator part being equal to 0. So we get S equals to this value. And if this is negative, then the zero will be in the right half plane. So two possibilities can occur. You can see in this. Uh, and the next part is for any input change, what functions of time will be included in the response. So the constant term and the exponential part will be included in that term. And is it bounded? Is the output bounded for any bounded input change? For example, ut equals m. So in this, if the input is m by s, the output will contain a term, t, and it will not be bounded then.
Is this clear? Is this clear to all of you? Any questions so far?
If there are no questions, then please try to do the third question.
Hello, sir. Sir, in the hello,
Yeah, go ahead.
sir. In the previous tutorial, we solved that like for calculating gain, we said that it's that limit s tends to 0 gs.
So there are various ways to do it. One is, so let's say k by tau s plus 1. What is the gain?
Okay, so
K.
k.
How do you get that k?
Sir, that's the general form.
Now, how do you get that k? If from k by tau s plus 1 to how to get k? Which essentially means that your substitute has to be 0, right?
Yes, sir.
Okay, so this is essentially, if you have a transfer function, there is no harm to get gain out of it. Substitute s is equal to 0. Okay, and if it is an input output, you would, what would you do? So you would calculate the rate of change of output by rate of change of input. So now, exactly what is your question? Could you tell me in what context?
So earlier we used that limit s tends to 0 gs for
Yes,
cal.
yes, yes. Now, and go to that answer B, G of S. So is that your doubt how that G of S is going? Is that, hello?
Um, Sir, I found out the g of s.
Huh.
So earlier we were solving for calculating the gain. We used to do that limit s tends to 0 gs.
Mm-hmm.
So, but here we are just looking at the standard form and then comparing and
No, it
uh,
is exactly the same thing, no? So let's say k by, so k1 tau s plus 1 divided by k2 tau s plus 1. Huh? K1 into tau 1 s plus 1 divided by tau 2 s plus 1. Okay, this is the standard form, correct? Is it not?
yes, sir.
Then put substitute s is equal to 0, what will you get?
K1 by K2.
No. So let's, what I'm trying to say, so if you look at this particular expression, if you look at this particular equation g of s, which is y of s by u of s, here there is a problem. Okay, that is why you ask, can gain be infinity? Is that the reason?
Yes, Yes, sir. Yes, sir.
Okay, okay, okay. So see that, so when you apply simplest form, right? So you have to make sure that your transfer function is rational. So don't apply those two cases when you have a 1 by s standalone in the denominator. Shruti,
Okay, sir.
if there is a 1 by s standalone, don't apply that condition. If there is at least uh, what you call, if so numerate denominator should have a s plus b form, then only you apply that. If there is an s being standalone, don't apply it. It would give you a very weird solution. Got it?
Okay, sir.
Otherwise, what you have to do is you have to take s out from the numerator, then cancel it out. Then also it would be very difficult because there would be 1 by s coming there, so it's going to be very messy out there. So the simplest way in those conditions would be convert into the standard form and equate. That's all. Okay.
Okay, sir. Thank you, sir.
Excuse me, sir.
Ah,
But we apply that limit to s into g of s, na? So s will multiply that side, so it will come out to be k1 only.
I'll tell you. So that is the final value theorem, right?
Okay, sir.
So I go ahead.
So in this question, first we have to write the standard first order time delay equation, which is k exponential minus theta s upon tau s plus 1. So this k is the ratio of steady state change in y to the size of input step change m. So which is equal to 1. And to obtain the other values, we have to see where the inflection point is, and then draw tangent on that inflection point, and um, the we have to draw a line at that inflection point, and the line uh, which meets at y equals to 1, uh, that's the first point, and the line when it meets y equals to 0, that's the second point. Um, so this part from here, this is tau, and this part, that's this whole line, that's theta plus tau. So you can get tau as 13 minus 1, 14 minus 1, that is 13. So this is how you will get the final uh, the final function.
Any questions on this? Any questions?
Sir, I didn't understand the part where K was calculated.
Okay, Sarthak, once again, please.
Okay, so you have to see that k is equal to the steady state change, and we can, from the diagram, we can see that change in y is equal to 1, and the step, sorry about the disturbance, and the step input, it's the input change.
Okay, so this is something I think we have not fully covered in the class. So this is generally called as first order plus time delay. So you know the model, right? So the first order plus time delay. So how do you get the time? You need to get the time delay and the time constants from the model. So the simplest way is, once you have the uh, data, fine. So you plot it. Okay, so you have the plot, which is this in the S shape. Fine. And so you have to figure out the regime where the slope is. So you have to figure out a regime where the what do you call, uh, just a second. So you have to draw a tangent at the point of inflection of the curve. So point of inflection is the point wherein the slope of the what you call the system changes dramatically. So here if you see the slope is in this direction, then it becomes flat, then it changes the other direction. So point of inflection should be somewhere here, and you have to draw a tangent, and the tangent is what is drawn here, and that tangent would cut the x-axis, and the point at which it would cut the x-axis is the from vertical origin to that is time delay. Okay, then the total distance, you see, and it would basically form a square here. So it would cut this, and it would also go and cut your maximum response, which is 1, and you drop a perpendicular down there. And so the total distance would be how much? So here it is 14 is what it would show here based on the profile. And you cut down what is the time delay, the remaining would be the time constant. Is that clear now?
Yes, sir, I understood the theta and tau part, but like how we calculated K is equal to 1.
Okay, so now, so what is the, so if you go to the question, please go to the question. So now who was asking that how K is 1?
Yes, sir.
Ishika. So now Ishika, you should tell me why K is 1.
Okay, sir, I got it. Fine.
Rate of change of output divided by rate of change of input. So change of output is 1 minus 0 and it is a unit step change. So unity, got it, no? One by
Yes,
one.
yes.
So maybe I think the last question we will stop at the moment because this is definitely not covered in the class. Uh, so maybe, yeah, so this we can probably take up starting from the next tune, okay? Because the fifth, I guess this is not covered, right? Let me check. So we have not covered how the, let me check my notes once. Teaching. Yeah. Give me a minute. Yeah, but I think still we can calculate. We all know how this. Let's discuss this. There is no problem. There is nothing unusual in this. We have learned the first order system. We know how its response works. We can still discuss it. No, not a problem. Go ahead.
Okay, so in this question, we know that it increases by 10%. So this could be our x of s, and try to find the time at which. Okay, so read the question and try to solve
So
it.
what is given? So you are given with a initial flow rate, then there is a sudden change, which is like a step change, and you got this profile, T versus H, which is the height versus time, and you have been asked to figure out the time required to find this 63.2 percentage, which is already we know, and find from. So see, we have been asked to find out the steady state gain and the time constant by using step A and step B. One using the output to reach 63%, which is like a time simple time constant, otherwise using the initial slope. So let's discuss both of that.
So should I share the solutions now?
After 5 minutes possibly.
Okay. So it can be described by a first order model. So the first part is we have to find the steady state gain and the time constant using these two methods. So the steady state gain is change in output by change in input. So the final value is 6.52 and the initial is 5.50. So that is change in output, and the change in input is given as 10%. So 10% of uh, this 30.4. So we use this and we get the steady state gain.
So any questions here? Anyone? Any questions?
So for the next part, we have to find the output. That is 63.2% of the total change. So we find the change, that is 6.52 minus 5.50, and 63% of that plus the initial value, we get 6.145 feet. So now this 6.145 feet, it comes between 6.07 and 6.18. That is t equals 0.6 minutes and t equals 0.8 minutes. So we have to interpolate between this to get tau. So this can be written, and tau comes out to be 0.74. So basically this we are interpolating between 6.07 and 6.18 feet. That's the 0.8 minus 0.6 and 6.18 minus 6.07, and 6.14 is the value at which we want, minus the initial, so 6.07. Is it clear?
Any questions? So what are we doing here? Have we got that? Anyone? Any questions?
So this is clear. Sir, I had some doubts in the previous tutorials.
Okay.
Sir, I could just again ask Sarthak sir if he stays back.
Perfect. Yes. So if there are some issues, yes, let's our Sarthak can address it. And yeah, I think that's all about it. Any other issues you wanted to discuss? Anyone?
Sir, I have also a doubt related to tutorial 2. So can I ask Sarthak sir for that?
Sarthak, would you able to take that up?
Yes, sir.
Okay, so let me know. So if there is some issue, please ping me in. I'm here. Okay.
Okay, sir.
Okay, guys, then discuss that without delay. Okay.
Hello. Yes, you can ask your doubts.
Yes, sir, I'll just share my screen. Sir, is it visible?
Yes.
All right, sir. So this is 2 to 1 question number 5. So we had to propose a feed backward model and a feed forward model.
Okay.
All right. So many a times, like we've seen that in mostly feedback models, we are just measuring the output variable and then taking that input and manipulating it. So will we call the output variable control variable in that case, or manipulated variable?
Um, what did you ask? Can you repeat, please?
Yes, sir. So we mostly see that in feedback control, we measure a variable, we see how it needs to be manipulated, and then after manipulating, we basically manipulate the same variable.
Hmm.
So there is no anticipatory thing included. So what I'm saying is that mostly we refer to as the output variable as the control variable. It's a value that we're trying to achieve. Uh,
Hmm.
but mostly in feedback models, we are manipulating the same variable to get the value we want. So in this case, will we call the variable a control variable or a manipulated variable?
So it will be called a control variable. In this case, they both uh, might be equal, but it will be called control variable only because in at the end you are controlling it. I mean, you are changing it as per your needs.
No, so control variable is something that we are trying to achieve the value of, and manipulated variable is something that we can physically manipulate.
Yes.
So either way, we will call it control variable only, even though we are manipulating it.
Yeah.
All right, sir. And sir, in this question, I wanted to ask, here we are measuring y, and we are changing the composition y as per whatever we require. And in case we have in case, yeah, can't we measure d instead? Will it be possible to measure d also and make the same changes, or we will only go with y? Y is the composition and d is the flow rate.
So you need you're saying that you want to measure D to change Y. Is that what
Yes.
you're saying?
Yes.
I think you can't change the composition by changing the flow rate, I guess.
Sir, in this case, we were in the feed forward model, we were measuring the input flow rate and
Mm.
change y accordingly.
Mm. So you, I guess you can do it then. You can measure D and then change it accordingly to change Y. I'm not sure about it, but see, you have to look at the equations, the particular equations. So in case of uh, Y, if there's a variable D in it, and then you're changing it to control Y, then it's possible. And if it's not, then not. You can't use it.
And so, what will happen if we, in this case, this is the model, what will happen if we change b or r?
If you change D or R,
B, yeah, B, will it not affect the other flow rates, or if
uh,
it will, how?
yes, it will change. You can do a simple mass balance that if F is coming in, R is also coming in, D is going out, and what about B? Can you move a little bit down? Yes, so B is going out. So by changing it, the flow rates will change.
Right. So in feed forward control, we could have changed either of, like if we are changing F, maybe we could have changed B. If they're viable, we could have changed B and R as well to get the required composition. Can we say?
I think you can change, but it would be better if you change F than B, because you can see the heat, the reboiler. You see that heat exchanger below the column, right? So that has something to do with B. So when you change B, that the duty might increase or decrease. So you have to look at the system in particular to actually change it. So it's better to change F. That's what I think. I'm not sure again about it.
Oh, all right. So should I stop the recording? It's still recording.